So, this is my last lecture in this workshop, and we have been looking at uh, linear programming, duality, and some applications of linear programming as well as the simplex method, and how it gives proofs of some interesting results in combinatorics. So, today I want to talk about a very interesting application of linear programming to coding theory. So what is this coding theory? So, basically suppose you call up someone and you want to tell them your phone number, and so you tell your phone number once and then you are not sure if they heard you. So, you tell your phone number again, and if they get the same number both times, then they are pretty sure that they got your number right. However, if there is a difference between what they heard the first time and what they heard the second time, then they know that there is a mistake and they might ask you to repeat it once more, and you kind of get the right number. So, this common sort of everyday protocol that we have is also the idea behind coding theory. So, we will just model it as usual as message being just a sequence of bits, so either 0 or 1. So in coding theory, funny color. So a message is a sequence of bits. And usually the message is sent in packets. So, maybe you will send 7 bits at a time or something like that. So a packet consists of n bits, let us say. So, your message is going to be some vector w in 0 1 to the power n. So, you can just think of it as a sequence of n numbers, each of them either 0 or 1. Okay, so suppose you have sent a message like 0 1 1 0 1, and so suppose you have 7 bits. Up to what, how many different messages can you send? Just 2 to the power 7, which is 128, right. So if you have 7 bits, 0 1 2 3 4 5 6 7. So there's 2 into 2 into 2, 2 to the power 7 total different objects, numbers, or whatever, different signals can be sent. But most communication channels have occasional errors. So, a 0 might get changed to a 1. So, as I was saying, you could try to avoid this by sending the message 2 times. So, I could do like I could send this 0 0 1 1 1 1 0 0 1 1 0 0 1 1. So, I just repeated each bit once, and so if there is an error, it is very unlikely that 2 bits next to each other will get flipped. Say the probability of an error is something like 1 in 100, then the probability that 2 adjacent bits will get flipped, assuming that these errors are independent of each other, would be 1 in 10,000, which is very small. So, if you sort of look at this message and it has this form that each bit is repeated twice, then you are pretty sure that it is a correct message. But suppose during transmission something got changed, one of the bits got changed, and say this 1 here became a 0. So, I instead of 1 I have like 0 0. So, so this second 0 is not an error. So, this is fine, you are seeing, okay, I got at the first step I got 0 0, then I got 1 1, then you see this and then you know there must be an error, right. But at this point you do not know whether the 1 is wrong or the 0 is wrong, it both are equally likely possibilities. So, you can't correct the error, but you know that there is an error. So, what would you do if you want to correct the error? Yeah.
What you have written 2 times? I have seen 3 once.
What? No. So, the original message was 0 1 1 0 1 0 1. So, 0 0 that corresponds to this 0, then this 1 1 corresponds to this 1, this 1 1 corresponds to this 1, but an error occurred and it became 1 0. Now, if you are receiving the message, you do not know which is wrong, is this 1 the mistake or is this 0 the mistake, right. So, now I am asking how would you be able to correct the error? In this case you can't, but can you think of a protocol which can correct the error? Send it 3 times, right. So, suppose I send 0 0 0 1 1 1 1 1 1 0 0 1 1 1 0 0 0 1 1 1. Then if one of the bits changes, say this 0 here becomes this 1 here becomes a 0, then I will know, okay, I will look at the other two and I will say, okay, in these 3, 2 are 1 and 1 is 0. It is very unlikely that 2 of them change. The probability of that is like 1 in 10,000, whereas the probability of one thing changing is 1 in 100. So, with a very high probability, I can say that this is the bit that is an error, and so I can read my signal from this triple this thing. So, the disadvantage here is that I need to provide a signal that is 3 times as long as the original signal, right. So, to correct one error, so to detect one error you just need to send things twice, but to correct one error this protocol requires 2 to the 3 n, or rather 3 n bits to send a message of size n. So, that is sort of quite inefficient, and turns out that you can actually do much better. So, very
Excuse
long
me,
is,
sir.
yeah.
So please, will you please summarize what we are doing? Because first we are coding in 2 and then we are coding in 3. So 3 is better now.
3 is better in the sense you can correct the error. If there is just one error, it can be corrected. It is worse in the
Okay,
sense that now the message has become much longer.
okay,
So,
okay.
so the transmission will slow down and the cost of transmission will go up.
But error correction is better.
Now, error correction is possible. Yeah, earlier error correction was not even possible, right. With just sending twice, you might know that there is an error, but you will not be able to correct it. And
Okay,
initially,
okay.
if you just send each thing once, you will not even know if this 0 changes to 1, you will not even know there was an error, right.
Yes, yes, yes.
So, so now the thing is, of course, there are other protocols where you just detect an error, and if you do not detect an error, you just assume it is correct, and if you detect an error, only then you ask for correction. But if it is a one way communication, you can't do that. So, you need to prepare your code in advance to be able to. Okay, so so there is this historical sort of discovery by Hamming that you can do things much more efficiently. So, so let me explain Hamming's idea. So, he came up with a list of 16 7-bit words. So, 16 means how many bits? 16 means 4 bits. So, by this original idea, if we wanted to transmit 4 bits allowing error correction, we would need to send 12 bits, because we would send each bit 3 times, right. But Hamming did a much better job. He came up with a list of 16 7-bit words. So, they are words, the original list of Hamming 1, 2, 3, 4, 5, 6, 7, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1. So, there is a list of such 16 words. Okay, I will just write a few more, I will not write the whole list, you can get it easily from the internet. So, a list of 16 7-bit words, and what is particularly interesting about this is that any two of these words. So, you take this word here and take this word here, they differ in at least 3 places. So, if you look at this word, this digit is the same, this is the same, this is the same, this is different, here there is difference, then the next one is also different, right, then these are the same, this is the same, then the next bit is different, right, and the last bit is also different in this case. So, these two words, they differ in 4 different places, but in general in this Hamming's list of 16 7-digit words, any two words will differ in at least 3 different places. So, he came up with a list of such words such that any two words. So, word I just mean a sequence of zeros and ones, differ in at least 3 different places, different digits, at least 3 digits. Okay, so, in 3 places, let me say. So, then what happens is, suppose there is one error, right, then you will know, okay, see this word is not in Hamming's list of 16 possible things. So, there must be an error, right, but also you can correct this error. Suppose I got something which differs from this by only 1 digit, say it I changed like this last digit got changed to a 0. So, I got 0 0 1 0 1 0 0. Now, remember that any two words differ from any other word in this code differs from this word in at least 3 digits, right, and here I have changed only 1. So, to get any other word I have to change 2 digits. So, if I know that there was only one error, this is the unique word that could have been transmitted to result in this word while making at most one error, right. So, I can correct one error using Hamming's code. So, this allows for correction of one error per what do you call it, token, per block of data. So, here what we are doing is we are able to send 4 bits with error correction, with one error correction, using total of 7 bits, which is much better than using 4 3s or 12 bits by the just repeat kind of trick. So, this is the basic idea behind behind Hamming codes and coding, modern coding theory. So, maybe we can try to now state it formally. So, so the idea is that you have all possible bits, you do not allow them all to be valid signals. So, in this in this example and also in the previous example. So, here when I am just doing the repeating, then the valid signals are those where the, say I am doing repeating twice, and the valid signals are those where each the first two digits are the same, the next two digits are the same, and so on. So, every block of 2 digits has the same digits. So, that is the set of valid signals. In this triple thing, the set of valid signals where every block of 3 has the same digits, and in Hamming's thing it is a little more complicated, but once you have this code written down somewhere, you know that okay, there are these 16 permissible words. Okay, so, formally we will just say that a code is a subset of 0 1 to the n. So, definition, a code is a code is okay, a code maybe I should say of length n. Is any subset C of 0 1 to the n. So, this Hamming's code n is equal to 7 and C consists of 16 carefully chosen words, right. So, 16 such things. And what do we want to do now? So, what we want to do is we want to see how many changes we can correct. So, we will think of each change as moving us away from the code. So, there is a notion of distance. So, this is called the Hamming distance. So, let me use a notation. So, if I have w between in 0 1 to the n, I will write w as w 1, w 2, w n. So, each w I belongs to 0 1. So, that is a word, w stands for word. So, the Hamming distance between two words, I will just call it d, d w w prime is the number of I between 0 and 1 and n, such that w I is different from w I prime. So, if one error has occurred, then the Hamming distance between the original signal and the transmitted signal will be 1. If two errors have occurred, then the distance between the Hamming the Hamming distance in the original thing will be 2 and so on. So, this measures sort of the number of changes you have to make to go from w to w prime. Okay, and you can also think of this in terms of bitwise components. So, alternate way of thinking about it is you define the Hamming norm of a word to be the number of I such that w I is not equal to 0. So, now this is this is actually the distance from 0 0 0 to w, right. So, the Hamming norm is just this thing, and you can think of the Hamming distance between two words as the Hamming norm of w plus w prime, where this sum is just component wise 0 1 addition, bitwise addition. So, 0 plus 0 0, 0 plus 1 is 1, 1 plus 1 is 0. So, let us just do an example. So, let us look at these two words in Hamming's code 0 0 1 0 1 0 1 and 0 1 0 0 1 1 0, right. So, this we already calculated, the Hamming distance is 4, right, and this is the norm of, you do the bitwise addition. So, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 plus 0 is 0, where was I? I have done 3, right. Okay, then the fourth one is 0, the fifth one is 0, the sixth one is 1 and the seventh one is 1. I am getting only third one is 1, is it? Oh yeah, third one is also 1. Okay, so this eraser is very big. Okay. So, this is not a 1, this is the norm. Okay, so clear, right, what is going on. And so, if a code allows you to correct errors, one error, then the Hamming distance between any two words should be at least 4. Yeah, thanks. Yeah, I mean 4 cannot be equal to 3. So, this is 4. I mean, we did this in two ways. I am just saying that it is the norm, Hamming norm of the sum. So, so the distance of a code which is denoted d of c is the minimum distance between two words in the code. So, what is d of Hamming's code? It is 3, right, and if you look at the simple codes we had earlier, the d of this double repeat code is 2, right, because any if there are two words in this code which differ at least in one place, then they will differ in two places because we are repeating each thing, and this triple code, its distance is 3. So, so what is the idea now? You want codes which are large and which have large distance, right. So, saying that the distance is more is putting a stronger constraint. If you say that a code has distance, I guess here I should say w not equal to w prime, because obviously if w is equal to w prime, then the distance is 0, right. So, any code will have distance at least no, any code. What is a code? It is just a subset of 0 1 to the n. So, take all the set elements of 0, at least one. So, because if you take two distinct words, then they differ in at least one place. So, every code has distance at least 1, and that is not very useful for error detection or correction. A code with distance 2 allows you to detect one error, a code with distance 3 allows you to correct one error. A code with distance 4 also allows you to detect and correct one error, but it may also allow you to detect two errors, right. So, and a code with distance 5 allows you to correct two errors. So, let me just explain this. So, if a code with distance 2r plus 1,
that also has to be consecutive errors.
no, there is nothing about consecutiveness here.
Like for 4-bit correction.
So, you look at
Excuse me, sir.
yeah.
Sir, the line which you wrote that we are able to send 4 bits with correction of one error using 7 bits. Please explain that line.
So, what's the, so if you have like 4 bits, then what you can do is you have 16 total different words in 4 bits, right. So,
Yes,
what you
sir.
can do is you can just list these 16 words in Hamming's code, and you can say, okay, this corresponds to 0000, this corresponds to 0001, this corresponds to 0010, this corresponds to 0011, and so on. So, what you are going to do is some sort of coding, you are going to take your original thing and turn it into a word in Hamming's code, and then you can if okay. So if we both agree beforehand that okay, this one corresponds to 0 0 0 0, this one corresponds to 0 0 0 1 and so on, then you can get that signal and you can decode it back, right. So, you just have to have a table which says which word corresponds to which 4-bit signal. But if there
Okay,
is
sir.
if there is an error, you are only looking at these 7-bit words and you can correct one error. I hope that is clear now.
Yes,
So,
yes, yes, yes.
with this
Thank you, sir.
protocol, so first we have to make a table. We have to make a table saying that these are the it does not have to be 4 bits. 4 bits is just a good way to measure the size, but if there are 16 people in this room and we want to just transmit which one of us is going to be eliminated in the next round, then we just have to send one of these words corresponding to each of those things, and if there is one error, you will be able to detect it. So, whatever 16 different possible words can be transmitted using 7 bits, but 16 different possible words sort of correspond to 4 bits. So, 4 bits of information is going in 7 bits. That's the calculation I am doing, and that is better than what we said earlier, where we were sending like 4 bits using 12 bits by repeating 3 times. So, the idea is to try to find a code with a large size and a large distance. So, let us just get this business clear. So, if C if distance of C is greater than or equal to 2r plus 1, then C allows for the correction of R errors. So, one way to visualize this is sort of as a spatial thing. So, you can think of these code words as forming a graph, and you connect two. So, let us just look at code words with 3 vertices. So, 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1, and we will connect 2 of these if they differ in just 1 bit. So, this is connected to this, this is connected to this is connected to this. Oh, sorry, yeah. So, maybe this is connected to this, and okay, what else is this connected to? So, I change the first bit, maybe that is a more systematic way. Change the second bit, change the third bit, okay, and then here I change the third bit, here I change the second bit, and now let us change the first bit, I will get 101. Then here I change the second bit, so let us change the first bit, I will get 110, and I change the third bit, I will get 011, and here I change. So, each thing will be connected to 3 others in this. So, if I change the middle bit 001, 010 and 111. So, this is already connected 100, 110, 110 here, and 101, right. And then finally, this thing is connected to 2 things, third bit, first bit. So, second bit 111, right, and then 110 I have connected to 2 things. This is changing the first bit, this is changing the second bit. So, I have to change the third bit. So, 111, and this is already connected. So, each thing is connected to 3 others. So, you can think of it as a graph, and now suppose I take suppose I take two, suppose I have, so in this case the maximum distance between two vertices is 3, right. So, for example, this 1 1 1 and 0 0 0, their Hamming distance is 3. So, if I take a word that is a distance 1 from one of them, so if I take any word here, it will be a distance of 1, if yeah. So, if I take any word here, then the distance from 1 1 1 plus the distance from 0 0 0 will be at least 3, I have, right, and it will be, so okay, let us think of it another way. So, suppose I am transmitting the signal 0 0 0 and one of the bits gets changed, right. So, it could go here or it could go here or it could go here, right. So, there are these 3 possibilities, this and this, but because the Hamming distance here is 3. So, okay, so what have I done? I have connected things which involve one bit change, and you can take the distance in this graph. That means, the Hamming distance between two nodes is the number of edges you have to traverse to go from one node to the other. So, the Hamming distance from 0 0 0 to 1 1 1 is 3, because any path going from here to here will go 3 steps at least. You cannot find a path which takes 1 step, right. So, now if you have changed one bit, then you are a distance 1 from here, you must have a distance of at least 2 from here. So, you know that you are closer to 0 0 0, and so you correct to 0 0 0, right. That is the basic idea behind this thing, that if you have code with distance 2 r plus 1, then it allows for the correction of r errors, because suppose you have a word w whose distance from some signal w naught is less than or equal to r, right. So, this is your correct signal. Then the distance of w from any other signal w naught prime will be greater than, so the point is that the distance between w and naught and w naught prime both are in the code. So, this should be greater than or equal to 2 r plus 1, and this is less than or equal to distance of w naught w plus. So, this Hamming distance has the triangle inequality. That is something you can easily convince yourself of, and if this is less than or equal to r, then this is greater than r, right. Is greater than r, which means that there is a unique point in the code which is within a distance r of the word w, right. Therefore, there exists a unique w naught in C such that distance of w naught is less than or equal to r. So, you can recover the original word uniquely. So, a code with distance greater than or equal to 2 r plus 1 allows you to correct r errors. Okay, so, now the question is, how big can I make? So, suppose I want a code on n bits which has distance say d. So, d may be 2 r plus 1 or any d, take an even d also. I want to know how big I can make this code. So, question is, how big can I make a code with distance d on n bits? Is the question clear? So, what does Hamming's code tell us? That I can get a code with at least 16 elements having distance 3 on 7 bits. Okay, so right, and maybe you can do better than Hamming or maybe not, but this Hamming's example is small enough so that you can easily run through everything by computer and see that actually Hamming's code cannot be improved upon. That is, you cannot find a code of more than 16 bits, more than 16 cardinal of size more than 16 with distance greater than or equal to 3. So, this A and D is defined to be, so this is the main protagonist of our story today, A and D. A and D is defined to be the maximum cardinality of C, where C is a code on n bits with distance greater than or equal to D. Okay, and we want to know what this is. So, what can you say about A? What does Hamming tell us? A 7 3 is greater than or equal to 16. In fact, turns out that A 7 3 is equal to 16.
Sir,
Yes,
Hamming provided the at least 16 or at most 16.
he provided a code of size 16. He provided a code of size 16, right. So, it is
Okay.
possible that you may provide me a code of size 17, right.
Okay.
Then that would end up making A 7 3 equal to 17.
Okay.
Okay, but
Thank you.
this is a small enough example, you can verify that it is actually 16, that you cannot find a code with more than 16 things. So, let us look at, let us try to understand this definition of A and D. So, let me ask you a very simple question. What is A n 1?
All of the
What is A n 1?
all of the codes should be there in distance.
Okay, so what is A n 1?
2 power 2 power.
So, A n 1 is 2 power n, the reason being that any code has Hamming distance greater than or equal to 1, right, because you take two different elements, their Hamming distance will be greater than or equal to 1. Okay, great. What about A n 2? So, any guesses? 2 power n minus 1, that is actually correct. How did you guess it?
You have to remove the big 2 because the distance is equal to 1. So, it will be there only when you are having one distance, like only one bit is different. So, it is just looking at the level 1 in the subset of all the.
So, can you I mean, so you are going to take all the words of length n, then how are you going to remove some of them
Some of them which are having distance equal to 1
from?
from 0.
Okay, good. So, one way to try to connect this, suppose that Hamming distance is suppose the distance is 2, and let us assume that 0 0 0 0 is in the code. I think you can always do that, because if some word is in the code, you just shift the code by that, and so let us assume that 0 0 0 is in the code. So, suppose 0 0 0 is in the code. So, let us say we are looking at n equals 4. So, now you have to look at words which are distance 2 from this.
1 from this.
You remove the things which are distance 1 from this. So, distance 1 from this means what? At least just exactly 1 1.
Just changing the remaining n minus 1 bits exactly at one time. Just changing the remaining n minus 1 bits exactly one time.
Remaining means, so what should I do now? I will change one of the bits, and those I should remove, right. So, I will remove words with 1 1. So, I will remove these 4 words 1 0 0 0, 0 1 0 0, 0 0 1 0 and 0 0 0 1. So, these are gone. So, I have now a code with 2 to the power 4 minus 4 words, but does it have distance 2? Maybe not, right, because for example, I still have 1 1 1 1 and I also have 1 1 1 0. So, I have to remove more things. So, the one thing you can do now is try to remove things with 3 ones also. So, remove things with 3 ones. So let us just take words with either no ones or 2 ones or 4 ones. So, words with an even number of ones. So it is not as simple as you were saying, but the idea is consider C equal to W in 0 1 to the n such that the Hamming weight of, I think it is called the Hamming weight of W is even. So, now if I have 2 words, if I have W has even Hamming weight and W prime has even Hamming weight, then W plus W prime will also have even Hamming weight, because just do mod 2 arithmetic. So, you add W plus, so if W is even, W prime is even, then W plus W prime is even, because addition mod 2 anyway preserves even and oddness, and so the distance of W and W prime has to be, well, W is not equal to W prime and W plus W prime, this is actually this, but since this is even, this has to be greater than or equal to 2 because it cannot be 1. So, if you take the code consisting of all words W with an even number of ones, that has Hamming, that has distance 2, and so that shows that A n 2 is greater than or equal to 2 n minus 1, because if you look at words which have an even number of things, you can think of it as a subspace of f 2 to the n, where you just take the linear functional, all add up the coordinates are 0. So, this is equal to V in f 2 to the power n such that the coordinates of V 1 plus V n is equal to 0. So, that is a subspace of codimension 1. So, its dimension is n minus 1. So, it has 2 to the power n minus 1 elements. So, but it actually turns out that, so what we have shown is that this is greater than or equal to 2 n minus 1, but it turns out that this is actually exactly equal to 2 to the power n minus 1.
Can you explain that again?
This subspace business. So,
Not the distance of the V1 plus V2.
So now instead of thinking of it as 0 1, think of it as F2, the field with 2 elements, and so then this code is also a subset of that vector space, F2 to the power n, right. F2 to the power n is identified with 0 1 to the power n, and what does it mean to have an even number of ones? It just means the sum of the coordinates. So, now instead of this 0 0 0 0, I am thinking of it as 0 comma 0 comma 0 comma 0, or I would have some vector 1 0 1 0. So, to say that it is even just means the sum of the coordinates is equal to 0, right. So, it is a vector space of dimension n, then you put one linear equation on it. So, I mean that means the kernel of a linear functional, one thing. So, the codimension is 1, which means that the dimension is n minus 1. So, it is just a subspace of dimension n minus 1. So, it has 2 to the power n minus 1 elements. So, a and 2 is 2 to the power n minus 1.
So we cannot drive the set property like that. Number of subset that we can use.
Yeah, so number of even sized subsets of the size n.
Suppose the distance is 1 means, so at least one changes must be there. So every possibility of subset I can form means 2 power n automatically will come.
Right.
Similarly, if I want the at least distance 2 means, I remove the one element is fixed, I fix it. Other elements already 2 power n, I want to remove the sum space. Suppose I fix, so automatically 2 power n minus 1 will come. Suppose number of subsets I want to make it, such a constraint directly will come.
So then by your logic a and 3 will be
2 power n minus 2.
2 power n minus, so that's not true actually. So those like 16 is 2 to the power 7 minus 3.
Yes, 2 power n, 4 means minus 1 I want. 1 means I will 2 power n, 2 means...
We are looking at a and 3. By your logic that is 2 power n minus 2, but that's not true. A 7 3 is 16. I didn't understand your reasoning, but I think there is an interesting idea there. So, so the idea is to try to use induction on n, right?
Yes.
Yeah. So actually, you can use that induction on n idea to prove this. So let me show you how to prove that. Okay, but there are some subtleties involved here. But the other thing is, let's give another proof that the size of this code is 2 to the power n minus 1. So, the size of this code is 2 to the power n minus 1. So, we are looking at things with even, right. So, then the question is what is the number. So, this just means that we are looking, each word corresponds to a subset of the set 1 to n, right. Just look at the places where you put 1. And so, you are looking at subsets of even cardinality. So, the cardinality of C is the number of subsets of the set 1 to n with even number of elements, right. So, that is n choose 0 plus n choose 2 plus n choose 4 plus so on. And this is actually half of, I will leave that for you to think about, n choose 0 plus n choose 1 plus, because of the is it, but if n is odd, then it is not quite symmetric. Yeah, I have a feeling this problem was there in my son's homework in class 11, but I don't know, just see if you can prove this. So, some binomial theorem variation, yeah. So anyways, so that is another way to do it, try to prove this identity. Okay. So, so this is not true, a n 3 is not 2 to the power n minus 2.
But then even number means it will come to, suppose if you want to take n, 2 means ultimately 2 power minus 1 will come, 2 n a n 4 means 2 power n minus 3 will come, sir. But the odd numbers only we have the face of problem.
No. So a n 4 is the same as a n minus 1 3, I believe. So it is not so easy. So you think about it a bit, but let me give you a proof of this. Okay, so let us prove this. So claim. So we already know that a n 2 is greater than or equal to 2 to the power n minus 1. I claim that it is equal to 2 to the power n minus 1. So proof is induction on n. So suppose C subset of 0 1 to the n, distance of C is greater than or equal to 2, and C has more than 2 to the n minus 1 elements. right. So, now you look at the words in C that end with 0 as you were suggesting. So, the last digit, right. So, you look at W in C such that W is equal to something times ending with 0. Okay, so, let us call this C 0 and W in C such that W is ending with 1. So, there are two subsets. Now, what we know is that the cardinality of C 0 plus the cardinality of C 1, these are disjoint obviously, is greater than 2 to the power n minus 1. So, what that means is that the cardinality of one of them is greater than 2 to the power n minus 2. For either I equals 0 or 1. But then that means that if I just take u in 0 1 to the power n minus 1, right, such that u I belongs to C I. So, if C 0 is if C 0 has cardinality greater than 2 to the power n minus 2, I will look at the words u such that u 0 is in C 0. So, this is also a set of cardinality 2 to the power n minus greater than n minus 1, because the same cardinality as C I, right. So, this let us call this C tilde. So, C tilde has cardinality greater than 2 to the power n minus 2, but what is the distance of C tilde? It is the same as the distance of it's at least greater than or equal to the distance of C, because if two words in C tilde have distance d, then to get the words in C, we are just adding I at the end, either 0 or 1 to both of them. So, the distance is preserved. So, the distance of two words in C tilde is the same as the distance of the two words. So, distance of u v is the same as distance of u I v I, and that is greater than or equal to 2, because these are in the original code C, right. So, this is, but this contradicts the induction hypothesis, because we assumed that by induction we can assume that this is a code, C tilde is a code in 0 1 to the power n minus 1, right. But then we know by induction that a code in 0 1 to the power n minus 1 with distance 2 must have at most 2 to the power n minus 2 points, but this is, so this is a contradiction. So, now some shocking news for you. So, just think about this proof, exercise, try to do this yourself. And now I have some very shocking news for you, and the shocking news is that A n 3 we do not actually know anything about it. So, A n 3 is known only for n less than or equal to 16. And I have not checked the current status, but few years ago the best known thing was that A 17 3 lies between 6 5 5 2 and 5 3 1 2. So, a range of more than 1000 for A 17. So, we still do not know the answer to this. You may think, okay, why can't we just brute force it, but then 2 to the power 17 is no, what is it? So, we are looking at codes. 2 to the power 17 is the number of words, and then we are looking at subsets of that, right. So, it is not, it is an astronomically large computation, you can't do this easily. So, this we do not know, A 17 3 is not known.
This is proved or
This is proved.
experimentally?
This is, so I will explain to you one technique for some techniques for proving these kinds of results, and we will be able to go up to 6553 using linear programming. So, but 6552, that one is harder to win. So, yeah. So, okay. So this is, this is an open problem, and we do not know, like, if your packets are 17 bits, how much you can send for correcting one error. So, yeah. So this is a big, sort of open problem in coding theory, and I do not think people even expect to get exact answers. The trick is to find good bounds. So one nice bound is called the sphere packing bound. So the problem is find good bounds for A n d. So that's the problem that we want to do. So so here's a nice technique. It's called the sphere packing bound, and this is sort of a geometric idea. So suppose I have a rectangular box and it's full of table tennis balls. Okay. So you can easily give an upper bound for the number of balls in this box, right? You know the volume of the box, you know the volume of the ball, and so you just say that the sum of the volume of the balls, so n times the volume of the ball should be less than or equal to the volume of the ball. It was not a very good bound because there will be so many gaps between the balls. So then you need to solve this other problem called the sphere packing problem to give a better this thing, but still at least you get something. So this kind of crude thing is called the sphere packing bound. So what we will do is we will try to break up the space of the space of all signals. So we are looking at the space, the box is now 0 1 to the power n, that is the space of all the boxes, the box, and then we are going to look at our code, which is a subset of that box. So at some points in that, but the fact that the Hamming distance between any two things is greater than or equal to d is sort of like saying that the ball has a certain space around it. Okay, but we will only do a counting argument here, we will not actually do any geometric computation of, so we will not see any 4 by 3 pi r squared or anything. So let us just, so it is called a sphere packing thing, but it is not exactly that, but the idea is similar. So let me just yeah, so so this I will assume that d is 2 r plus 1. So let C be a code in maybe I should write it, let C subset of 0 1 to the n d of C greater than or equal to 2 r plus 1. Okay. So now what I will do is I will define a ball, my table tennis ball with center at a point w. So BWR is just those things, points in 0 1 to the n such that d of w prime is less than or equal to r. So I am looking at all those words that can be obtained from w by changing at most r bits. Okay, so if w is such a code, then these are disjoint, right. So if C, if DC is greater than or equal to 2 r plus 1, then the sets BWR W in C. So if I take W1 and W2, two distinct points in C, right, then they will be disjoint because I have W and I have W prime and the distance. So I am going distance r from here and I am going distance r from here, these cannot coincide, because if this were common point, distance r from here and distance r from here, that would make the distance between w and w prime 2r, but I am assuming that the distance is greater than or equal to 2r plus 1. So, these are pairwise disjoint. So, all two of them are disjoint. So, now we get a very easy thing, right. So, we have so many balls, how many points in BWR? Just 2 to the power r, right. No, 2 to the power r times, no sorry, not 2 to the power, what is it? I want to change, I have a sequence of n things, I want to change r of them. So, how many are there? At most r. N choose r, but I can also change fewer of them. So, n choose 0 plus n choose r. So, what I get is that cardinality of C times summation j goes from 0 to r n choose r. So, these are so many disjoint sets is less than or equal to 2 to the power n. So, this is 2. So, that means that the cardinality of C has to be less than or equal to 2 to the power n divided by j goes from 0 to r n choose, not n choose r here, this should be n choose j, right. N choose j. So, let us see what this gives for what way we look at A 7 3. So, 2 to the power 7, what is it? 128, 35 is 32 is 5, 6 is 64, 128. R is now 1, right, because D is 3, one error is being corrected. So, I will take 7 choose 0 plus 7 choose 1. So, 128 divided by 1 plus 7 8, which is 16, which is exactly Hamming's code. So, this proves that Hamming's code is the best. You will not be able to find one with 17. Okay, but you can try this A17-3 using this, and I think it gives something quite a bit larger. Let me see if I wrote it down. So, it gives A17-3 is 131,072, apparently that is 2 to the power 17, and the denominator will end up being 18, and this may not be exactly divisible, but this gives 7281, and the best known bound is 6552. Less than or equal to, sorry, this is also less than or equal to. This just gives an upper bound. So, we can't do better than we cannot so hope for something with more than 7281, but okay. So, here is a linear programming kind of. So, this is a bit complicated in the sense it does not give you a quick formula. Okay. So, I am going to give you another way to get a bound, and it is called Delsart's bound. This is also somewhat old, and it really has not been improved much. This Delsart's bound will give us 6553. But what this Delsart's bound will say is that to find an A and D, we must, it will set up a linear programming problem. It will not tell us the answer, it will set up a problem and then you solve it and find the bound. So, it is that sort of thing. So, so here is Delsart's bound. it's a very clever idea. So, so for so we have n and d, we will fix for integers 0 less than or equal to I and t. For I and t between 0 and n, put. So, the statement itself is really funny, k t n I to be just some number, j goes from 0 to the minimum of I and t of minus 1 raised to j, I choose j, n minus I choose t minus j. Okay, some funny number, and then for all n and d, a and d is bounded above by the optimal value of the linear program, maximize x 0 plus x 1 plus x n subject to x 0 equals 1. Sorry, this looks a little silly, but x I equals 0 for I equals 1 to d minus 1. So, these are not really variables, they are fixed, and the remaining are variables, and there are some linear constraints. I goes from 0 to n, k t n I x I greater than or equal to 0 for t equals 1 to n. And we also have the constraint x 1 x n greater than or equal to 0. So, if you want to compute a 17 comma 3, then you have this linear, well, a priori 18 variables, but 3 of them are fixed, right. X 0 is 1, x 1 is 0, x 2 is 0. So, x 3 to x 17, there are 15 variables, and there are 17 inequalities. 17 inequalities, easily something you can run on a computer, and if you have a lot of patience, even by hand. So, maybe no, I am not sure about that. Anyway, so for A 17 3, this gives optimal value is turns out to be exactly 6 5 5 3 and 3/5. So, that means that 6 5 5 3 is actually an upper bound, which is just one higher than 6 5 5 2, which was took of several years to improve by 1. So, this is a very weird sort of statement. It is not giving the answer as such, but telling you that okay, you can compute this answer at least for some values, and so using this you can get bounds for many more n and I, and the bounds are, or at least in the 17 3 case it does a pretty good job. So, so what is the idea behind this Delsart's bound, right? So, we will call this program I do not know, let us call it D, D not for dual, but D for Delsart. Okay. So, what is the idea behind this Delsart's bound? So, the idea is that suppose you are given C, a code, then we will associate to this code some variables x 0 tilde, x 1 tilde, x n tilde, such that the distance such that the cardinality of C is x 0 tilde plus x n tilde. That is what we want to optimize, right. So, we will introduce some numbers associated to the code, so that the cardinality is of the code is the sum of them. So, we will basically partition the elements of the code into pieces which will have size x 0 tilde x 1 tilde, and then we will show that when distance of C is greater than or equal to d, then x 0 tilde x n tilde are feasible for the program D. That is the proof strategy. So, what is the x I tilde? So, we will just define x I tilde to be 1 over cardinality of C times the number of pairs w comma w prime in C squared, such that the distance of w and w prime is equal to I. So, now if I add over all I, then what do I get? I get all pairs w and w prime in C squared without any condition on the difference, right, divided by cardinality of C. But that set has cardinality C squared, divide by cardinality of C, I get a set of cardinality C, right. So, this is absolutely clear right away, right. So, that so clearly x 0 tilde plus x I tilde equals 1 over cardinality of C times cardinality of C squared, which is equal to cardinality of C. So, this thing is clear, right. Then what were the other conditions? The condition was x 0 tilde is equal to 1, is that clear? Because you will just take w comma w, the only way distance between something and something else is 1, is that they have to be the same, is 0, the Hamming distance is 0 if and only if both the words are the same, right, no bits have changed. So, then we are looking at w comma w, and then what about x tilde I, where I is less than d? Well, this d of w w prime has to be greater than or equal to d, right, because the code C has distance d. So, if d of C is d,
minimum.
yeah, d of w w prime is greater than or equal to, is greater than or equal to d for all w w prime w not equal to w prime in C. So, x tilde I is equal to 0 for I goes from 1 to d minus 1. This is because d of C is greater than or equal to d. So, you cannot have 2 points in C whose distance is less than d, right, and that is what I am ruling out, 1 to d minus 1. Okay, so, this first few constraints of the Delsart program are clear up to here. So, this is the tricky business. Of course, these are greater than or equal to 0 because they are just counting something, and we are not doing an integer relaxation or anything, we are just going to solve it as a real linear program, which we can do pretty fast, and then we take the integer closest to it as the bound. So, yeah, so what about this business? So, this is slightly tricky, so let me try to explain that in the last few minutes. Okay, so remains to show that, remember the definition of k T n I is some j goes from 0 to min I t minus 1 raised to j, I choose j, n minus I choose t minus j, and the constraint was need to show that summation I goes from 0 to n k t n I x tilde I is greater than or equal to 0 for t. That is those are the remaining constraints in this del Sart program. Okay. And this is a cute little argument. So, yeah, so here's so it requires a little bit of work. So, firstly this lemma that if I look at the number of w comma w prime in C squared. Okay, so I need a definition first. So, suppose I have a subset I of 1 to n, then I can define the Hamming distance between two words relative to I. d I w comma w prime is equal to the number of I in I such that w I is not equal to w prime I. I can also define the Hamming weight of w to be the number of I in I such that w I is not equal to 0. So, of course, this is equal to Hamming weight w plus w prime I. Okay, so, I am just generalizing this Hamming weight and Hamming distance, where I will ignore the bits that are not in the subset I. So, here is the here's a lemma such that the distance relative to I of w comma w prime is even is greater than or equal to the number of pairs w comma w prime belongs to C squared such that the distance is odd for all I. So, not only is it true for the Hamming distance, also true for all relative Hamming distances. So, slightly more general statement. Okay, the proof is quite nice. So, let us define the things with even Hamming weight. So, E let us just E be the set of W in C such that W I is even. By the way, this I claim is true for any code. Okay, there is no hypothesis on the code here. That's yeah, and O is W in C such that wait a second. The Hamming weight relative to I is odd. So, now if you look at this d I w w prime, this is even if and only if both w and w prime belong to E, right. If both w and w prime have even number of bits differing from 0, then they have even number of bits differing from each other, and or w w prime belong to O. So, if both have even or odd, and its odd means what? If and only if one is even, the other is odd. So, W belongs to E and W prime belongs to O, or W belongs to O and W prime belongs to E. So, this cardinality of this set cardinality of LHS. So, maybe instead of rewriting everything, is cardinality of E squared plus cardinality of O squared, right, and RHS is 2 times cardinality of E cardinality of O. Of course, this difference is just the square. So, yeah, minus. So, that is so what is going to happen is we have to prove this thing which involves these signs, and these signs are going to be these even and odd bits, and we are going to show that something is greater than or equal to 0 will correspond to this statement. So, I claim a corollary here is that for every code C, so these are unconditional for any code without saying anything about the distance, and any vector v or any signal v in 0 1 to the power n, we have the sum over w prime belongs to C squared minus 1 raised to. Now, if I just take this d of w prime, right, then this will be greater than or equal to 0 according to this lemma, because the plus ones will come from the distance being even and the minus ones will come from the distance being odd. I will just tweak this a little bit, and I will say instead of this I have this vector v, I will think of it as a vector in f 2 to the n, and I will say w plus w prime transpose into v. So, if v were actually equal to 1 1 1 1 1, then this would be exactly that, but this is also true in general, and this is just because you just take instead of you just take I to be I in I such that V I is equal to 1, then this is precisely what you get. This lemma becomes this inequality, because the positive terms will come from those things whose distance relative to I is even, and the negative terms will come from those pairs whose distance relative to I is odd. So, that is all it is. Okay, so, this with this we are ready to finish the proof. So, what we have is this, right. So, now we will just sum over all vectors v. So, what we get is summing over all v in 0 1 to the power n, we get summation w prime in C squared summation v belongs not maybe not all vectors with. So, it is true for every vector, but we can just take vectors whose Hamming weight is t. V belongs to 0 1 to the n, Hamming weight equals t minus 1 raised to w plus w prime transpose v. This is greater than or equal to 0. Now, what we will do is we will group this according to the sum w plus w prime. So, what we get is setting u equals w plus w prime. We can write this as a sum of u in 0 1 to the n, and then sum over v with Hamming weight t, and now this is just minus 1 raised to u transpose v, but then we must count the number of u, the number of pairs w comma w prime in C such that w plus w prime is equal to u. Okay, just simple rearrangement. So, this will turn out to be that binomial coefficient business that we wanted. So, so we will now, so let us say that this u transpose v, this is what the number of common ones in u and v, right. So, suppose u transpose v is equal to j, this is equal to yeah, and let us say that number of u, the Hamming weight of u is equal to I. So, I suppose I have this information that u has I ones and u and v have j ones in common, then I should be able to easily count the number of words w and w prime in C let us see. So, but they have to be in C. Okay, but I only want an inequality. So, suppose we want to say yeah. So, suppose I want this thing, right. So, I have fixed V and V has size t, right, and I want to find out how many no, let me say this. U has size t, let me write it one sec. What was the condition? They may not do it like this. One sec, I sort of, this part of the proof is slightly clever. So, what is this? Minus u transpose v, and I am taking the sum over minus 1 to the power u transpose. Okay, so this is still this w comma w prime in C squared, and this is okay, I guess, w it's okay, I guess. So, let me just see. Getting a bit confused. So, the size of V is so size of V is t, okay, size of u is I, and I want this. Okay, so let us see the number of u such that u transpose V is j. So, so u is of size I, V is of size t. Then how many how can I construct u of size I such that u has U has j ones in common with V. So, V has T ones, right. So, U has I ones. So, out of the I ones of U, I must choose okay, let me write down this equation. I should have. So, summation V in 0 1 to the n such that V is T minus 1 raised to U transpose V is equal to, now suppose U has j things, j equals 0 to min I t and minus 1 raised to j, and so out of those I things which are 1 in V, I should choose j, and out of the n minus I things which are not in V, I must choose t minus j. And so, what we are saying is that this is the so what is this is just k t this is k t n I. So, anyway, maybe I did not explain this very carefully. So, if you do this carefully, what you will get is summation w comma w prime in c squared k t n d w w prime is greater than or equal to 0. And the number of times, how many times does k t n I appears in the above sum? It is just, so we are looking at distance should be I, right, but x tilde I is the number of pairs with distance I divided by cardinality of C. So, it is just cardinality of C times x tilde I. So, what this becomes is sum over I k t n I x tilde I is greater than or equal to 0. So, the main idea behind this proof is this parity thing, that the even distance things are more than the odd distance things, and so this alternating sign in k t comes from there. So, anyway, I think you know, I did not do justice to this proof, maybe I need a little more time to explain it properly, but you get, I hope you get the general idea. You can look it up in the book of Matusek and Gartner. But this is, I found a very fascinating use of linear programming to give a way to compute an upper bound for the A and D as an optimal solution to a linear programming problem, and it gives almost the best bound for 17,3, A 17,3. Alright, that brings us to the end of my course in this workshop. So, couple of things. So, I will send out an email. We are required to have you all fill out some feedback forms, and I also want you to fill out the information for the certificates. So, you fill out your name, your affiliation, and we will email a PDF certificate to the email address that you fill out in that same form. Okay. So, fill it out exactly as you want it in the certificate, and do not put all caps for your name and so on, it will look bad on the certificate. So, it will be done exactly as you fill it out, and feedback forms, please, one feedback form for each instructor, but it only takes 2 minutes to fill out each feedback form, and one feedback form for the whole program. So, I will send you that also. Okay, so yeah, so that's it for now. I hope
Thank you,
that,
sir.
yeah, hope that you got something new, some new things out of this course, and gives you some idea of, like, you know, how linear algebra is used in sort of very different ways from what we traditionally imagine it to be used in. You know, we think of it as something geometric, but in all these courses we are trying to show how it is actually also has other aspects related to understanding data.